Denny's criterion asserts uniform convergence of arbitrary functions. False. Denny's criterion asserts uniform convergence of monotone functions. False. Denny's criterion asserts uniform convergence of a monotonic sequence of continuous functions. I think that's true. Lots of conditions. The functions f sub n of x equal xn converge uniformly to the null function on 0, 1. We showed that in class, right? They all look like what? If you graph them on 0, 1, that's the first parabola, the second cubic curve. They all start to look like this, but you can never pull the 1 down, right? So in the limit, the pointwise limit is 0's over here, and then at 1 it is 1. That's a discontinuous function. So if they were uniformly convergent, each one of those is continuous, you'd have to have them all 0 function, but you don't. So not true. If Fn with the double arrow, which means uniformly convergent, if Fn converges to F on AB, and Fn is continuous on AB, then the limit then goes to infinity. The Cauchy integral is the Cauchy integral of the limit. That's, I think we proved that Thursday, didn't we? That you can commute integration and taking limits. So that's the convergence theorem for Cauchy integrals. You may, under suitable conditions, the limit of a sequence is the sequence. Sorry, the limit of an integral is the integral of the. What am I trying to say? This is what I'm trying to say. This is the Cauchy integral of the limit. Is the Cauchy integral of the limit function. You take the limit on the outside. It's the same as the limit on the inside. There needs to be an n here. Yeah, subscript, I dropped it. Fermat was able to integrate power functions x to the alpha for alpha greater than -1. We showed that in class. It's true. Where? No, the limit as n goes to infinity f sub n of x. Here the limit is outside the integral. Here it's inside the integral. Oh yeah, there should. Yeah, I just didn't know the answer. Sorry,
That's Dean's theorem. That's Dean's.
This one?
Yeah.
That's not Dean's theorem.
Yeah, the limit on the inside.
Well, hold on a minute. We'll go over about Dean's theorem. This is the theorem that says you may integrate term by term, a series. Remember, a series is a sequence of partials. So if you integrate the terms in a sequence and take the limit, you get the same result as if you take the limit first and then integrate. That's this theorem. That's not Denny's theorem. It's close. Yeah, well, we're talking about uniform convergence. That is a theorem by Denny.
Okay.
But it's not Denny's theorem. Yes. But don't worry. Okay. Yeah. In Wade is calling this Denny's theorem. Denny's criterion is somewhat different. I'll explain that in a minute. Okay, now I see why you were confused. This apparently, Denny was a guy that was Ulysses. He investigated the phenomena that are associated with uniform convergence about 100 years ago or so. And he has a weak converse to the proposition that a uniformly convergent sequence of Denny's functions is continuous. You can turn that around, but you have to add some additional properties. Denny's criteria is this. If you have a pointwise limit of continuous functions, and continuous functions have to converge monotonically. In other words, they either have to all be going up or all be going down. It doesn't matter, all up or all down. Point-wise monotonic convergence on a compact set. And if you know in advance that the limit function is also continuous, then you may conclude that the convergence was uniform. That's Denny's criteria. Okay, now I see why you're confused. I'm confused. Yes, this is, we'll call that Denny's theorem. That's when we get to Lebesgue's theory. That's one of three key theorems for Lebesgue integrals. Called Lebesgue's dominated convergence theorem. You can interchange those. Okay. The Dirichlet salt and pepper function is Lebesgue integral. Yes, a famous example. Yes, it's true. The Dirichlet salt and pepper function is hence not Kurzweil. We did that day 2. The Eudoxian axiom holds in any Archimedean field. You had to be paying real close attention. What was the Eudoxian axiom again? You have two quantities. It was that thing that was stated in the sort of traditional.
Two quantities, one is real small, the other is very large.
Yeah. You can keep chopping that large one in half and then that in half. Eventually it gets small. So in other words, given any two positive, they were positive quantities. The way the Greeks said, let two quantities be set out. And of course, for them, that meant positive. You take the larger one and you keep dividing by 2. Eventually, you get below the small. That's the Eudoxian axiom. And using that, well, what did he prove? Well, he proved the business about the circles. So the areas of the circles being the same ratio as the squares per radii. So an Archimedean field is a field for which the following is true. If A and B are positive elements in the field, some multiple of A is true. I guess I should call it a Eudoxian. It's essentially the same thing. Okay. So it doesn't matter how small a positive fraction I have and how big a number I have. I can keep multiplying the tiny little fraction by some ginormous number, and eventually it will exceed a pre-assigned larger number, everything being positive. That's the hallmark of an Archimedean field. Can you prove that in an Archimedean field, whereas an Archimedean field was a field first of all, you remember what that is from algebra, and it's also an ordered field. So there's a concept of a positive set and a negative set, zero set, right? Can you show that there is no smallest positive number in an Archimedean field? See if you can. That would be a good exercise. I should like that problem. So the Eudoxian axiom, yes, sir, it's essentially the same.